Shubha? Any other clarifications?
Yes, clear.
Today, we are going to take the experiment number 3, which we missed during uh, the break. Still, some students are missing to write these informations. Try to write this properly. And this section is 104. Today, we are performing this experiment. Right? The date on which you are doing this experiment. Now, let us come to the actual experiments. Experiment number 3, Archimedes principle. Anyone have an idea about the Archimedes principle, Shiba? Do you have any idea about the Archimedes principle? What is Archimedes principle?
No idea.
Okay. Suppose if you take an object, lift the object in the air. Suppose one of your friend, you are lifting one of your friend when in the air, on the floor, you can say. Sometimes you cannot be able to lift the person because the person is bit heavy. The mass is bit higher. The weight of the object is bit higher. You cannot be able to lift. Suppose when the persons get into the water, now it is completely immersed in the swimming pool water. What happened? Now you are going to try to lift the person when both the persons inside the water. Now you can be able to lift the guy. Why? You feel there is a reduction, there is apparent reduction in the mass of the person, or you can say there is apparent reduction in the weight of the person. The the weight is equal to mg, the mass into gravity. You know, the gravity is a constant at any point on the surface. Any changes, we are not accepting the changes in g. If there is any changes in w, the weight, the changes should be given to the mass, right? The g is a constant. If there is a change in the weight, can I say there is a change in the mass? Shiva? I can say there is a change in
Yes,
the mass.
doctor, we can say it.
Now, is there any change in the mass really happen to the person?
No.
Whatever the content the person has on the floor, the same content, same material present with the boy when it is immersed in the water. Two legs, two hands, everything the same. But how the mass is reduced? The reduction in the mass was not a real reduction. It is apparent reduction. Apparent means it is not really true. But you feel the reduction. The reduction is true. At the same time, the mass did not reduce. Then what happens? How you feel there is a reduction in the mass without changing the mass of the object. The mass of the object does not change, but you feel the change. Where from you get the feeling of reduction in the masses? When you put the object inside the water or any fluid, now the fluid exerts a force on the object from all directions. From all direction, the force is exerted on the object immersed. When it is completely immersed, the pressure at the top is less than pressure at the bottom. PB, the pressure at the bottom is greater than pressure at the top. And this we will study in chapter 14. Now, the net force exerted by the object, by the fluid molecule of the fluid's molecule on the bottom surface of the object is greater than the force exerted by the molecule on the top surface. Now, if you find the net force exerted by the molecules on the object, then you will find there is a real net force acting in the upward direction, right? Acting in the upward direction. What is the total weight of the person? It is mg, is acting down. Here, some force is acting up. Sigma Fy is equal to 0 because the object is in the equilibrium position. It is not moving up or down. Now, what is sigma y? It is FB. FB is called as a buoyant force, the net force exerted by the molecules of the fluid in the upward direction. FB minus mg equal to 0, right? Can I say mg, that is W, is equal to FB? Shubha? mg
Yes,
equal to
Doctor.
FB. What is FB? FB is the buoyant force, the force exerted by the molecules of the medium, molecules of the fluid, I can say. The molecules of the fluid in the upward direction on the object. FB equal to mg. Yes, the buoyant force is the net force exerted by mg. What is mg? Is the weight. The weight WW is the weight of the displaced water. What is the displaced one? Suppose if you fill the water until the full maximum level of the bathtub. Now the water is completely filled. Now, when you get into the bathtub, what happened? When you get into the bathtub, what happens? The water overflown. How much water overflown? That depends on the volume of the person, volume of the object immersed completely inside the water. Why the water overflow? Right? Why the water overflow? If you fill the gas with a tight container, when you get into the gas will not overflow. But the water overflows. Why? The reason is the fluid, liquid, any liquid I can say. All the liquids are incompressible. What do you mean incompressible? You cannot compress the fluid, but you can compress the air. How can I say this? If you take a water bottle, now there are two water bottles. One water bottle is empty, no water inside. No water is inside. What is inside now? Air. Now you tight the mouth of the bottle filled with air with a cork tightly. Next bottle, other bottle is completely filled with water. Now you want to crush both the bottles. Which bottle you can able to crush? With the air or with the water, Shiva?
The empty one with air.
It is not empty.
Yes,
It is
it's
inside, the air is filled. You
yes,
cannot say it is empty.
the air one.
The air. But one bottle number one, air is filled inside the bottle. The bottle number two, the fluid, liquid is, the water is filled. But you can crush the bottle in which the air is filled. That means you can compress the air. The air is also the fluid. You can compress the air. Can you able to compress the fluid, the water bottle? No, you cannot compress. This is the important property of the fluid, that is incompressible in nature. And this incompressible in nature leads the usage, the application of the fluid in the hydraulics, the hydraulic jacks. There are many hydraulic machines. All the hydraulics machines work based on this principle, incompressibility of the fluid. Okay, let me come to here. Yeah, when the object is get into the water, the some amount of water is overflown. How much water is overflown? The volume of the overflown water is equal to the volume of the object immersed in the water. This is one of the findings of Archimedes. Now, the buoyant force is equal to the weight of the displaced fluid. The weight of the displaced fluid. I told when you want to lift your friend in the air, it is difficult to lift your friend when he is on the floor. It is filled inside the air. When the same person get into the water, you feel the mass is reduced. How much mass reduced? The apparent reduction of the mass is equal to the buoyant force. Sometime back I already told you. And FB is also equal to, the buoyant force is also equal to the weight of the displaced water. Now, can I take this, the last two line? And m air, that is m air into g, that is w air. M water, the mass of the mass of the object in the water into g, that is the weight of the object in the water. Now mwg, what is mw? Mw means the mass of the displaced water. When you put an object inside the water, when it is completely immersed, it will displace some amount of water. The mass of the displaced water into g. I can cancel g throughout. Now what happens? Mw is equal to m air minus m water. What is mw? The mass of the displaced water is equal to mass of the air into mass of the air minus mass in the air minus mass in water. Now, if these two sides are equal, then you can say the Archimedes principle is verified. We are going to check this formula, this equation in this experiment. Mw is equal to, what is that? We are going to do this one. Mwg is equal, Mw equal to m air, m water. What is Mw? Mw is rho w, Vw. What is this? The rho is the density. Density is mass per volume. If you want to get the mass, take the volume this side. Yeah, mass of the water, displaced water, is equal to the density of the displaced water into volume of the displaced water. Now you got the right hand side. The left hand side. The right hand side you can get by subtracting the weight of the objects in the water from the weight of the same object, mass of the object in the air. Now the density of water is 1 into 10 to the power of 3 kilogram per meter cube. But here we are going to use the value 1 gram per centimeter cube. Why? Because you are maintaining all the units in this experiment in gram and centimeter cube. Therefore, we want to express the density also in the similar unit, so it is easy to cancel the similar units. First, I want to measure the volumes. Let me go back to the objective of this experiment to verify the Archimedes principle using series of regular and irregular shaped objects. We are going to verify the Archimedes principle for various shapes. Some shapes are regular shape, some shapes are irregular shapes. We are going to verify our Archimedes principle for these shapes. Total, there are 6 shapes given to you as per the schedule. The 3 symmetrical shape, that is cylinder. 3 different material which is in the cylinder form, and 2 blocks and rectangular shape, 2 different rectangular shape. The last one irregular, it has no regular shape. If the 3 objects, the first object is in the cylindrical shape, is made up of aluminum. The second object is also cylinder, but it is made up of brass. The third object is also cylindrical shape, but the cylinder is made up of plastic. 3 different type of material used to make the cylinder here. The next rectangular shape, that is block. There are 2 rectangular shapes. One is made up of brass and second one is made up of aluminum. The last one is aluminum irregular. That piece of material is made up of aluminum. It has no regular shapes. Out of 6, 3 are cylindrical shape and 2 are rectangular. The last one is irregular shape. If the shape is regular shape, then we have a prescribed mathematical formula to calculate the volume. We are going to use that method. How to do that? The volume of the cylinder is equal to pi r square h. This is the formula to calculate the volume of the cylinder. Phi is, the constant, r is the radius of the cylinder, and h is the height of the cylinder. All the three cylindrical shape, you have the same formula to calculate the volume. Only thing is we have to measure two quantities, the radius and the height. The next two shapes are regular shape, but it is in the form of in the shape of a rectangle. The volume of the rectangle is L1 into L2 into L3. The three lengths are different. To calculate the volume, multiply all the three lengths, you will get the volume of rectangular shape. The last one, irregular. We have no mathematical formula. No mathematical formula to calculate the volume of irregular shapes. Now, how we are going to get that? We are going to calculate the volume of the last one, irregular shape, by using Archimedes principle. I will explain this a bit later.
Doctor,
This is the first data I'm going to collect. Yes, Shiva?
I have to put this formulas in my paper.
Yes, I will tell you later.
Okay, but now, Doctor, I don't have.
Wait, gentlemen. And the next one is the second part of the experiment. This is the verification of the Archimedes principle. The first one, first we are going to measure the mass of the object in the air, the mass of the object in the water. The rest is calculation. Only these two columns, we are going to collect the data. Based on this data, we are going to analyze and find the values for the other column. I told there are 6 shapes of the objects given to you. Out of 6, 5 are regular shape. Out of 5, 3 are cylindrical shape, the 2 are rectangular shape. The last one is irregular shape. Now take the aluminum cylinder, measure the mass of the aluminum cylinder by using the triple beam balance. I'll show you a video how you can handle the triple beam balance. And suspend the object in the air, measure the mass of the aluminum cylinder in the air. Now, immerse the aluminum cylinder completely in water. Now, you find there is an apparent reduction in the mass. Now, you can measure the mass of the same aluminum cylinder when it is completely immersed in water. Now, m air minus m water. Can you find the difference between these two? M air minus m water. This is the apparent change in the mass of the object. VW, what is VW? The volume of displaced water. When you put the aluminum cylinder inside the water, it completely immersed. When it is completely immersed, it displaces some amount of water. What is the volume of water displaced by the aluminum cylinder is equal to the volume of the displaced water. By Archimedes principle, it says the volume of the displaced water is equal to the volume of immersed object. The volume of the displaced water is equal to the volume of immersed object. Now, in the previous slide, we calculated the volume of different shapes of the object. When it is completely immersed, the volume of these pieces is equal to the volume of displaced water. Now, copy this volume to this schedule. VW equal to cm centimeter cube, volume of displaced water. The
Doctor,
next column, yes.
here we put what we calculated in the
Yes,
upper
the previous
box.
schedule, copy the 6 value to the schedule.
Yes.
And rho W equal to 1 gram per centimeter cube. Because we are keeping everything in gram. See, the mass in gram and volume in centimeter cube. Therefore, we are writing the density also in the similar unit. And rho W equal to 1. And rho W into VW, since rho W equal to 1, you will get the same answer here. If you use a different fluid, the rho W will be different, therefore the next column will be different. For liquid, water, it's the same. Then theoretically speaking, right, this m air minus m water is equal to rho W VW as per our equation. Theoretically speaking, these two should be the same, but experimentally, they may not be the same due to many reasons for that. And we are going to find the error, the percentage of error introduced in the measurement of this. How can you measure the error, percentage of error? Now, if you go to the next page, there is a formula. Using this formula, I'm going to calculate the percentage of error. Rho W VW, last but second column, minus m air minus m water, I think fourth column, divided by rho W VW plus m air minus m water into 100. This absolute value gives you the error percentage. Can you write the error percentage here? You are writing the error percentage. You are repeating this experiment for different shape: brass cylinder, plastic cylinder, brass block, aluminum irregular. We are calculating the percentage of error in each every row. Clear?
Doctor,
And yes,
the column of VW and rho W VW will be same?
for the water it is the same.
It's the
For
same.
different liquid, this will be different.
Yes, yes, I know.
For
But
water, it
here,
is
but here it will be same values.
yes, yes.
Okay.
So we'll talk about the source of error and conclusion later after discussing the analysis, and this also I will discuss later after seeing the video. Now I will share you the video. You can watch it. You can learn how I am handling the equipments and get the data. Archimedes principle, experiment 3, and some sections they miss this experiment due to holidays. This week we are going to do this Archimedes principle. The objective of this experiment is to verify the Archimedes principle using Archimedes principle, experiment 3, and some sections they miss this experiment due to holidays. This week we are going to do this Archimedes principle. The objective of this experiment is to verify the Archimedes principle using series of regular and irregular shaped objects. We are going to verify the Archimedes principle for regular shape and irregular shape. Some shapes are going to have the regular nature, and some objects of the irregular shape we are going to verify the Archimedes principle. Come to this, the Archimedes principle, there will be apparent change in the mass of the object when the object completely immersed in water or any fluid. And actually the mass does not change. The mass of the object does not change. But you feel there is a change. That's why the word we are calling it as apparent change. You feel there is a change in the mass of the object. In how much the mass changes, we observe is equal to the mass of the water or the fluid displaced. This is the actual Archimedes principle. This FB, it is the buoyant force. The buoyant force is a force exerted by the fluid on the object in the upward direction. The buoyant force FB is equal to Wn, the weight of the object in the air, minus weight of the object in the water. And this is the weight of displaced water. WW is weight of displaced water. Now, on simplifying this, we got m air minus m water into G. That is this. And this m air minus m water into G is this expanding this m into mass into gravity is WW is in the MW G. MW is the mass of the displacement. On cancelling G on the other side, we get MW is equal to m air minus m water. The mass of the object in the air minus the mass of the object inside the water when it is immersed in the water is equal to the mass of the displaced water. If you place the object in the water, it displaces some amount of water. And what is the mass of the displaced water? Is equal to the mass of the displaced water equal to rho W into VW. What is rho W? It's the density of water, and VW is the volume of displaced water. And we are going to use this to calculate this. And rho W is equal to 1 into 10 to the power of 3 kilogram per meter. And this is the density of pure water in SI unit. But in the gram per centimeter, and rho W equal to 1 gram per centimeter cube. We are going to have the different shapes of the object. These are the regular shapes. These are regular 3 cylinder, 2 rectangle, made up of different material. The first one is made up of aluminum, is made up of the plastic, is made up of brass. And this rectangular shape made up of aluminum is another smaller rectangular shape made up of brass. And if you have one more shape, this is irregular. Shape. First, we are going to calculate the volume of all the shapes. For first 5 shapes, 5 regular shapes, we have a prescribed mathematical formula to calculate the volume. First, we are going to record the volume of all regular and irregular shapes in centimeter cube. Yes. And we have a prescribed mathematical formula to measure the volume of regular shapes. There is no mathematical formula to calculate the volume of irregular shape. First, let us calculate the volume of regular shapes. Now we have the schedule. These are 3 regular shapes. The first aluminum cylinder. The first schedule is for cylinder. Aluminum cylinder, cross cylinder, plastic cylinder. Radius, first we are going to measure R in centimeter, and height of each cylinder, height h in centimeter. The volume of the cylinder can be calculated by using this formula pi h r square. Pi is the constant, you know it. H is this, and R is this. We are going to measure, the first one is aluminum cylinder. Take aluminum cylinder, and this is a vernier caliper. We are going to measure using vernier caliper. The diameter you can measure. You can look at this, and this is the diameter. Here we are going to take the values. This is a 2.2. This is 2.2. 2.2 centimeter is diameter. Diameter radius is 2.2 divided by 1. The radius is 1.1 centimeter. I noted down the radius is 1.1 centimeter. I'm going to measure the height of the cylinder. The height of the cylinder, then keep this in between these 2 jaws.
Doctor, why 1.1? You said 2.2.
Now we are measuring the length of the aluminum cylinder. Now look at here. 2.2 is diameter. Shiva?
Yes.
2.2 diameter. What is the radius? Diameter divided by 2.
Oh. Okay. Okay.
Right? We are recording the diameter. Sorry, radius, not the diameter.
Oh,
yes.
he wants only the radius, the half.
Here we are measuring the diameter. Where is that?
The full.
Here I am measuring the
size.
diameter.
Okay.
The height of the cylinder, then keep this in between these 2 jaws and measure the height of the cylinder. Now we are measuring the length of the aluminum cylinder. Now look at here. It is 6.35. Now I am recording the length of the aluminum cylinder as 6.35 centimeter. The next, take the cross cylinder. I am going to do the same thing and measure the radius, the diameter first, and from this radius and the length of this cylinder. Repeat this experiment for the next cylinder, that is a plastic cylinder also. Record all the values here, all the radius, all the height. By using this formula, you can calculate the volume of each cylinder. Come to the next shape. The next shape is brass block. Brass block, I'm going to measure the length L1 in one direction, L2 in another direction, L3 in the other direction. So take this brass block, measure the length in one direction. That is 2.6. 2.6 is the length in one direction. I recorded as length 2.6. And the next, the length in other direction. This is 1.9. 1.9. I recorded this as 1.9. And the length in other direction is 1.6. 1.6, I recorded as 1.6. The next, to take the aluminium and measure the length in one direction. This is 1.6. And the length in a different direction, this is 3.15. 3.1. And the next, .85. Now I can write it here. Now all the 5 shapes are completed. You can measure the volume of each shapes by multiplying L1, L2, L3 and complete. Now copy this data to this table. The volume of each regular shapes, you can copy it here. And last one is missing. The volume of the aluminum irregular. Irregular, we don't have any formula for that. First, fill the water. Now you pour the water. The water is released through this, and the water will be filled up to a particular level. Wait until the last drop released from this. Wait for the last drop. Now it is removed. Now empty this. Empty the beaker. Empty and keep it here and place the irregular inside this. Now it displaces the water. The water displaced is transferred to this beaker. Wait until all the final drops enter into this, until the water dripping stops. Then you have to take the graduated one. Wait until the last drop lands on the beaker. Now it stopped. Transfer this water and check this one, the graduated beaker. It should be empty. And transfer this water very, very carefully. Now all the water transferred to this carefully. Now you can get the values. It's not clear, you can take the background. Now you can get the volume. The volume from this level. Now note that as your volume of irregular shape. The volume of irregular shape you can note down.
Doctor, the volume is the height of the.
Now this part is moved. Yes.
The volume of the regular shape here is the length of the.
Yes, the water.
There.
Yes.
Yes. Okay.
Now we are going to move to the next part. We're going to use the balance, and this is our next part. The aluminum cylinder we are going to take. You measure the M air. There's a mass in air, mass in water. Find the difference. And VW, the volume of displaced water. You can take the volume of aluminum cylinder from this table. And then rho W, VW. Rho W equal to 1 gram per centimeter. So you will get the same answer. The error percentage can be calculated by using this one. Represent rho W VW minus M air minus M water divided by rho W VW plus M air minus M water into 100, take the absolute value. And by using this formula, you can calculate the error and write the error value. The error value expected to be as low as possible. Before starting the experiment, we have to set the triple B balance. The triple B balance. Ready? And this, and you have to adjust this. The mark should show 0. Now, the first is aluminum cylinder. Take the aluminum cylinder and hang it over here. Measure the mass of the aluminum cylinder in air. Adjust this. Now, adjust this so that we'll bring back to the 0 level. Now, come to 0, then note down this 55.8. 55.8 gram is the mass of the aluminum cylinder in air. Now you are going to place the same aluminum cylinder inside the water and measure the mass again. Place the aluminum cylinder inside the water. Now the aluminum cylinder should be completely immersed in water. Now look at here, the mass. I'm going to adjust the balance so that we'll bring back the mass to the 0 level. I'm adjusting this to get back the mark to the 0 level. Yes. Now I got that. The mass, note down the mass. This is 35.4. 35.4 is your 35.4 is the mass of the aluminum cylinder water. Then you can find the difference between these two. And VW is the volume of aluminum cylinder. You can copy from the previous schedule. And rho W is 1. And multiply this and find the error by using the formula. The next to change the aluminum, repeat the experiment for draw cylinder, plastic cylinder, brass block, aluminum block, and aluminum irregular. For all the shapes, first find the mass in air and then suspend the materials inside the water. The object should be completely immersed in water and then measure the mass of each object while it is immersed in water. Then find the difference, M air minus M water, and you can copy the volume of the displaced water is equal to volume of the material from the previous schedule. And rho W equal to 1. The rho W equal to 1 gram per centimeter cube. This is in gram per in terms of gram per centimeter. Then you can get this and find the error by using it. There is no graph in this experiment. The source of error, the major and minor source of error right is here, and the conclusion, the argument response flow is verified for the given shapes of objects, and then write that the error, the percentage of error varies from here, find the minimum error and the maximum error. First give me this.
Doctor, how we can get the conclusion again? The
I will
error?
show you later.
Okay.
Okay. Any doubts, Shubha? Now I will tell you how to make the calculation. First, let me take this. Okay. The aluminum cylinder, we have the formula to calculate the volume. Is it right? Pi r square h. Pi r square h is the formula. Now let us find this. Pi is 3.14 into h 6.35 into 1.1 square is equal to 20. It's coming. It's 24.126. Second also will get the same, 24.126. The last one, 6.32, right?
Doctor, in my calculation, I have got 24.138.
I am getting like this, 24.012.
Please, Doctor, check.
I am doing it with the calculator, Shiba.
Also me, Doctor, and the
I am doing it with the calculator.
24.14.
The next is 1.6 into 1.9 into 2.6.
What?
This is 7.904. L1 into L2 into L3. 24.444. Now you calculated the volume of all the regular shapes. You can copy all the volume to this schedule. Is it clear? Copy all the volume. And only one volume I did not copy there.
Doctor, did you use
Yeah.
the symbol of pi in your calculator, or just put 3.14?
3.14.
3.14.
Yes.
Because when I use the symbol of pi, I got the result.
Okay. 24.012. 24.012. This is This is 24.904, 24.4, 24 point. Okay. Now I'm going to share you the data. You can copy the data on your paper. After copying the data, then I will tell you how to make the calculations. Now it's the time to copy the data onto your paper. Did you get this, Shiva? Can you see this?
Yes.
Yes, Doctor.
Copy the data onto your paper.
Please wait, Doctor.
Yes. Doctor,
Yes.
in page number 4, you want us to put it in the
Yes,
experiment?
you calculate there. From there, you can copy from here. That is the main source
Okay.
place for calculation. This is just recording place. This is Faraj Mubarak is sending a lot of data. Dot 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 dot. What is that? Faraj Mubarak Almari. What is the meaning of dot?
Doctor, the irregular shape,
Yes.
how you can get the volume of it? The height of that?
Did you watch the video?
Yes, yes.
Yes. From there, you can get the answer for that.
From that water, doctor. You speak.
Pardon? I hope you copied this. Go to the other part and copy this data also. Only two columns have the data, and the rest we are going to calculate.
Victor, can you back for the previous data? The last column, yeah. Thank you, Doctor.
You can copy this.
What is PW, Doctor?
Rho W is the density of water equal to 1 gram per centimeter cube.
Doctor, please, what's the volume of the aluminum irregular again? From up 13.20. Okay, okay.
Doctor.
Yes.
And the first one, the error percentage, I got it in minus. I put it in positive.
Okay, wait, I will come. If anyone copy it, then explain this. And this one, m air minus m water 65.2 minus 40.2 is equal to 25. Am I right?
Yes.
25.
Yes, doctor.
Yes, the red color you did not write. And VW. VW is the volume of aluminum cylinder, that is 24.126. 24.126, you can copy from there. And rho W is equal to 1. Rho W is equal to 1 gram per centimeter cube. If it is 1, you will get the same answer, right? If rho W equal to 1, you will get the same answer. Now the error percentage. The error percentage can be calculated by using this formula. Rho W VW minus m air m water divided by rho W VW plus m air minus m water. Rho W VW, what is here? 24.126 minus m air m water, this 25, divided by 25 plus 24, yes, 24.126 into 100. I have to take the absolute value, that is 1.78%. Right. If you look at this, and there is a line front and back of the numbers, therefore that means you would have to take the absolute value. You can repeat this calculation for every rows, right? Every rows you can repeat this calculation, and in this experiment there is no graph. We are not going to draw the graph for this experiment. The sources of error and the conclusion. What are the major and minor sources? Though we did not calculate the percentage of error, but we are going to talk about the source of error, major and minor source of error. The main source of error in this experiment is in the measurement of mass of the regular and irregular shapes in air and water, and the calculation of volume of regular and irregular shapes. Both we are doing manually, and these could be the major source of error. The minor source of error in this experiment is in the value of density of water. Density of water we have taken as 1 gram per centimeter cube. That is for pure water. Whatever the water we are using in the laboratory may not be pure. The density may not be exactly equal to 1. If there is any error introduced in that, we assume it is minor. The conclusion. The Archimedes principle is verified for regular and irregular shapes given. There are 5 regular shapes and 1 irregular shapes given, 5 various regular shapes. And we verified the Archimedes principle for this, and the error varies from the last column we found the error. The error varies from, that is a minimum value of the error, to the maximum value of the error. It's clear?
Doctor, the maximum or the last number?
The small number to the last number.
To the maximum number or the last?
Yes,
maximum
number.
Not last number.
Minimum to maximum.
Mm-hmm.
Hello, doctor.
Yes.
Sorry, I go to the bathroom and I didn't. I have the picture of the data, but can I know how to calculate?
Doctor,
Yes.
in the conclusion, you want us to write the volumes for each shape?
No, error.
Okay.
Okay. Thank you, Doctor.
Okay.
دكتور الدكتور
Yes, coming.
should I calculate the average source of error or not, or
No,
the
no.
okay?
No, minimum to maximum. It varies from 2. I did not report the average percentage of error. You can see your report. You can visit the office, visit my office, and you can see the report and find what are the mistakes you have committed. On Monday and Tuesday, the entire day I will be available in the college.
Doctor, the error
Yes.
you wanted 2 decimal accuracy.
Yes, minimum 2 decimal. That is no need to tell every time. That is the default.
Okay,
2 decimal accuracy.
okay.
Shabab, I'm telling you, you can come to the college and see your paper, your report, and find what is your mistake.
Can we leave, Doctor?
If you know mistakes, sorry, no doubt, you can. There is no graph for this experiment.
Okay, thanks.
Okay.
Doctor,
Yes.
if I got 0.025,
Hmm.
I have to put 0.03 or 2.
0.025. 25, 23 you can, sorry, 03 you can.
I can, okay. Doctor, or I can use 0.02 either.
Both are right. Since it is 5,
Yes, 5.
0.02, 0.03, both are 5. Because the 5, you can go this side or other side. You have the freedom.
Okay, okay.
دكتور
Yes.
the column before the error BW VW.
Yes.
How do we get this?
If you multiply one with the next column, you will get the same. That means the previous column and this column same.
Okay.
Rho
Okay.
W equal to 1.
Okay. Thank you.
Mm.
Doctor, can we leave?
Yes. 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 Yes.
Doctor,
Yes.
0.30, no problem. It's like 0.3,
0.30. Okay, no problem.
no problem. Okay. Because doctor, I got 0.295, so I can.
Okay. Yes.
Okay.
Doctor.
Yes.
How do I calculate the error percent?
Use the last formula in the last page.
In the last page?
See this formula.
Yes, I see it. I'm sorry.